Okay, it is time to start. So I will get started here. What we're going to do is I'm going to lecture on the lab as well as the concepts that are involved with the lab. Then we're going to take a pre-test, and then we'll actually do the lab. So getting started here, we were just about to talk about physics last class period. I talked about the difference in speed and velocity with jargon and the weight versus mass. And so with physics, we're looking at nature in all realms. So the scale of what we look at in physics varies incredibly. When we get to the end of second semester, we're actually going to be looking at quantum physics things, and we'll be looking at details of what's going on with minute things. And so this picture here was very famous when I was in graduate school. It was made when I was in graduate school. That was obviously done by IBM. And what they did was they used a very sharp point to pick up atoms and move atoms and made that IBM out of the atoms. That's pretty sophisticated to be able to move individual atoms to make something, to design something. And of course, physics gets out to as big as, okay, I'm going to turn the volume down because that's a lot of background noise. Not sure what it is, but astronomy is studying incredibly large things. All of that is within the realm of the sizes of things we're looking at in physics. Of course, for most of this class, we're going to be dealing with the size of things that we see every day in life. So an important thing here is units. Units tell us how big something is. If I were to tell you that it is, 3/4 from here to my home, you'd be, well, what does that mean, 3/4? But if I said it's 3/4 miles from here to my home, you'd be pretty clear on, okay, I know what the distance is. So in physics, it's really important that we don't forget to say units. If I say, okay, I'm 6'3", you probably know what I mean. But it's better if you're precise when you say 6'3", then you know, yes, that's what it is. So units are important in our lab. Anytime you have a number, you need to put units with it. If you don't put the appropriate units with the number, you'll lose credit there. Okay, it's a very simple thing. It's not like we want to take credit away, but we need to make sure that you're actually recording things in a usable way. A second thing that goes with units is, well, what units do we have? So some of the basic units we use, time. And everybody knows time, seconds, minutes, hours, days, months, years. Some of these are based off of very regular things, like a year is the time that it takes for the Earth to do one orbit around the sun. Right? It's based on a very simple thing. The month is roughly based on the time that it takes for the moon to do an orbit around the Earth. You get to hours, minutes, and seconds, and those are a little more obscure in where they come from. So the standard unit for time is the second. So you use hours, minutes. That's a conversion from the second, and everybody's good with it. But the standard, the SI unit, is a second. And since 1967, that second has been defined with a very precise measurement, so you can determine what a second is in any lab in the world. You just have to have the right equipment, and you can create this transition in the cesium atom. At 0K is obviously not really possible, and you can get what the second is. So we have a very reproducible calibration for a second so that the second has real meaning. And so an atomic clock is a clock that is actually using an atomic transition. It doesn't have to be this one that's defined on the atomic transition to actually measure the time. We often call clocks like this atomic clocks. They're really radio set to an atomic clock. But since they're being controlled by an atomic clock, that's why we call them atomic clocks. Now, distance, I gave the distance to my house, and I said it was 3/4 of a mile from here. Very convenient. Until I got married, I always walked. But, once you're married, okay, my wife would get really angry if I said that. So that's not the standard unit for distance. The mile is, I don't know actually the origin of the mile. We don't pay attention to the mile that much in physics because it's not useful to us. We don't use it. What we use in physics for our standard is the meter. And the meter's origins are pretty obscure. They decided to take the distance from the North Pole to the equator, and I think that was 1,000 kilometers or something like that. And then they estimate, okay, so a meter must be this large. And so then they took a piece of platinum iridium bar and they etched 2 lines on it. So the distance between those 2 lines is 1 meter. Of course, you have to keep it at the same temperature or it expands or contracts. The problem with that is, if you wanted to have a meter stick and see is that correct, you would have to take that meter stick over to France where they're storing this and compare it. It's not a very useful standard. So in 1983, I guess here we had my definition of the meter. I could have just read the slide. But who reads the slides? Show of hands. In 1983, which is when I was in high school, they defined the meter to be exactly the distance light travels in 1 divided by 2,997,92458 seconds. And so why they in vacuum? Why they do that? Because now you can, if you can measure the time accurately, you can then determine the meter accurately anywhere on Earth. You just make a vacuum, shine light, and figure out that distance. Of course, it's not as easy as I just said, but it's doable. So our standard for distance is the meter. In this class, we're always going to use meters. Now, mass is the last of our 3 common units. First semester, we will only have 3 base units: time, distance, and mass. I talked in class yesterday about the difference in mass versus weight. Mass is a measurement of how much stuff is present. And the standard for mass is this ingot of platinum iridium. That's an alloy of 2 metals. And so if you want to get a calibrated mass, you have to go to France where they have this thing sealed in a double vacuum. You can see there's one vacuum chamber that has its edge there and another one that has its edge here. A double vacuum chamber, they have this mass, and you'd have to take it there and get permission to compare the masses to see if you're really 1 kilogram. It's not reproducible. It's not a good standard. But we don't have anything better. Scientists are actively working on trying to find a way to get a standard mass that can be reproduced in a laboratory setting. So our 3 standard units that we will be working with essentially this entire semester: time in units of seconds, distance in units of meters, and mass in units of kilograms. And you're reasonably familiar with all of those, I'm guessing. The name for the system we use is called the metric system, or the Système International de... Okay, I can't pronounce French. Do you need us? Something like that. So that's what we call the system. There's another one that is sometimes used. You'll see that's called the CGS. CGS is centimeters, grams, and seconds. And so it's still based on the metric units, but a centimeter, centi is a prefix that means 100th. That's why there are 100 cents in a dollar, because cent means 100th. The gram is what's used in the CGS system. What did I say was the standard for mass? The kilogram. The kilogram is unique in that we have the prefix there. 1,000 grams is the standard for mass, not the gram, but the kilogram. And then, of course, seconds is still the same. And if you use the CGS system, you end up with units for like dynes for force and ergs for energy. So if you ever see dynes and ergs, they're units in the CGS system instead of the meters, kilograms, seconds, MKS. So here are all of the standard units. These are all of the base units we have in physics. Everything else is derived from these units. So the ones that we will be studying this semester exclusively, well, actually, I guess there's temperature as well. The meters, kilograms, seconds, and temperature we measure in kelvins. And, of course, we'll study kelvins later on. I'm not going to worry about it. Most people know what it is. Charge, surprisingly, is not a base unit. It's current, the rate at which charge is traveling, that is the base unit. And so the ampere is the base unit. The reason the ampere is the base unit is because it's, once again, something that's reproducible, measurable in the laboratory. You put 2 wires, 1 meter. That's not me making all the noise, is it?
No, I think the students are sitting by a microphone, okay. So maybe tell them that they're sitting by a microphone that they need to.
Yeah. Yeah, if you're sitting by a microphone, if you could not make as much noise, that'd be good. Okay, so back to this. You just have two wires that are separated by a meter, and you measure the force per unit length, and just adjust the current until you get a certain force per unit length, and that's an amp. So it's very reproducible in the lab. That's why it's the standard. You guys know about, probably you've already taken chemistry, so you know about moles. That's a standard unit. And finally, for light intensity, we have the candela. Those are the base units. Well, what about the standard things we use in physics? I mean, most people know force is a standard thing we talk about in physics. Well, the units of force are a derived unit. It's a unit that's made up of other units. So the unit of force is the kilogram meter per second. See if this actually highlights what I want to highlight today. There we go. Kilogram meter per second squared. Excuse me, I said second, forgot the square. So that's the unit of force. It's so common that we have a name for it. We say 1 Newton, capital N for Newton, named after Sir Isaac Newton, is equal to 1 kilogram meter per second squared. But when you're doing manipulations with units and equations, you need to know that a Newton is a kilogram meter per second squared so you can cancel units appropriately. Now, many people here are like pre-med. And so if you're pre-med, you have to take the MCAT exam. And they will have some questions on the MCAT exam that are simply about units, like which unit's equivalent to this? And you have to be able to go through and use these derived units to cancel units and whatnot to find what the actual unit is for a calculation. There's a standard down here, the last bullet. When we talk about Sir Isaac Newton, of course, we capitalize the N in Newton. When we talk about the units of force, a Newton, we don't put a capital N. So that's a way of distinguishing between the person and the unit named after him. But for the symbol, we still use a capital N. Because, you don't want to make it super straightforward. We do want it to be straightforward. We want physics to be as easy as possible. But you can't make everything simple. One word that kind of troubles me in homework is the term factor. So I just put this slide in so we make sure we know what it means. If we say something increases by a factor of 2, that's real simple. It doubled. But if we say it decreases by a factor of 2, to me, that's not as clear. Decreasing by a factor of 2 means you divide by 2. Just want to make sure that nomenclature is understood in case that comes up in a problem. So decreasing by a factor of 3, 1/3. This here is just a little beginning of basic math, just to make sure we understand that things aren't as simple as they would seem. When I was teaching at PUC, our pay scale is based on a percentage of a standard. And one year we went from 150% to 152%. And our financial vice president, with a straight face, honest as can be, he said, "That's a 2% salary increase you got this year." Going from 150 to 152 is going up by 2, but that's not a 2% increase, right? And so this here is just to make sure that we have some understanding of how this works. If you have, and I'm going to have a slide after this with a clicker question. If you don't have a clicker, or if you haven't registered today, whatever, don't worry. This isn't going to count against your grade. It's simply so people can check and see, I can tell you who answered and who didn't after class if you're curious, did my answer get registered? But when you have something like a 50% off sale and you have a coupon for 50% off of the sale price, some people might think that it's free because 50% and 50% add up to 100%. That's 100% off. But that's not the way it works, right? You do 50% of the first number to get a second number. And then you do 50% of that to get the third number. And so you actually have 50% of 50% is 1/4. And so 1/4 the price is still probably pretty good unless it's super expensive. So when we talk about percents, remember percent, cent means 100. So percent means per 100, 30%, 30 divided by 100. Now this is of course my first time trying to do a clicker question since, I thought I'd start this. Since we went to the new clickers, but here is our question. Suppose you own stock valued at $100 per share when the market opened on Friday, but it dropped by 50% on Friday. Thankfully, it rose by 50% today. What is it worth now? You got a question?
What channel?
Okay, this is channel 33.
If they have a license.
Yeah, if you have a license.
And Richard, I accidentally muted. I'm not accidentally. I muted Southwestern, and I don't know how to unmute them.
For people Southwestern, you may not have heard that. Somebody else muted you. It wasn't me.
So is that the session ID?
The session ID. Good, especially for the people at Southwestern. They're not going to know this. The session ID is PHYS Web, if I remember correctly. I think I can actually view that. Yeah, no, it's Web PHYS. And it will be that session ID every class period.
Can Southwestern ask the question? Because I don't think we're unmuted like Skip thought, or Kip thought we were.
Let me.
Southwestern, can you talk? Ask them.
It sounds like that's a no. Yeah, I cannot unmute them. I didn't do it.
No, I didn't. That was my.
Excellent. I guess you guys can't ask questions. I'm sorry.
Well, yeah.
Okay, I am going to go ahead with the stopping the answers here. This, like I said, this isn't going to count against your grade today. It's just to see how many people actually have them registered and can get them in. And so we had a total of 10 responses. There are, I think, 18 that are registered, so that seems odd. And all 10 of them said $75. They're correct because you simply took $100. Hey, they're back.
Oh, I think one of the guys had pushed it on his microphone and thought he was helping things.
Okay.
Over there.
So $100 times 50%, so 0.50, gave you $50 was the value of the stock after the market closed on Friday. And then you went $50 and it went up by 50%. So I'm going to multiply by 1.50, the one for its initial price, the 0.50 for the increase. And 50 times 1.5 is $75. Everybody who answered got it right, but it's always useful to go through and see the work. Okay, some quick history of how physics was developed. If we go back to, 300 odd years before the birth of Christ, we have Aristotle, one of the great thinkers, and he did a lot of work trying to study the natural world. But one of the interesting things from our perspective about how he analyzed the natural world was he looked at things and he said, what would explain why this is working? And if it was a beautiful explanation, it had to be true. He judged the value by how beautiful it was. So, for instance, he believed that all of the planets were doing spherical orbits around the Earth. Why spherical? Because he thought spherical was the perfect shape. And he thought it was perfect out there, so it had to be spherical. And they were rolling around on crystal spheres, not crystal like, not iron crystal, but quartz crystal. Why quartz crystal? Because he thought it was the perfect material. That's how he came with his ideas. It wasn't by doing experiments, but by trying to think about it and coming up with things that he thought were beautiful. Then we get to Galileo Galilei. I just love to say both of his names. Now, Galileo was instrumental in changing some of the fundamental beliefs that Aristotle had given us, like that model of the planets doing circles around the Earth. And Galileo is credited for being the first person who said, we need to study what actually happens, do experiments to test what happened. So one of the things Galileo is famous for of course, is dropping the 2 balls off the Leaning Tower of Pisa. Now, how many people know that story? Wow, not nearly as many as I expected. Well, the funny thing about that story, like I mentioned this morning, Newton with the apple falling on his head, probably not a true story, probably not something that really happened, but he used it as an example. Aristotle believed that if you dropped something, that everything was made up of a combination of just 4 elements. Well, unless it was outside of Earth, then you had the quintessence, the 5th element. But those 4 elements were Earth, which has a natural position of down in the ground. Then you had water that has a natural position of lying on top of the Earth. And then you have air, which natural position is up here above the water and the Earth. And then you had fire. And if you have a fire, while the smoke goes up, so I believe fire must be the top thing. And so if I take something like, view this quick clicker, and I drop it, this clicker is made up of a certain amount of earth, and a certain amount of water, and a certain amount of air, and a certain amount of fire. So I drop it, and it falls down because the natural position for Earth is on the ground. It had enough earth that it wants to get down to the ground. And the more earth it has, the faster it's going to fall. That was Aristotle's idea. So if you make something with twice as much earth in it, it should fall twice as fast. Unless, of course, you put more air in it that would make it try to hover, or more fire in it that make it try to go up. So that was what Aristotle believed. And now I look at that and I think, that doesn't make sense. Why? Because, well, I've learned from people like Galileo. And so Galileo did experiments with incline ramps. That is, he'd set up a ramp and put something on here and let it roll down and measure the time for things to roll down and compare the angles and compare sizes and that kind of thing. And he determined, no, Aristotle wasn't right. And so as an example of him showing Aristotle wasn't right, he proposed, if I were to go to the top of the Leaning Tower of Pisa and I had one ball that's twice the mass of another ball and I dropped them both, what would happen? Now, according to Aristotle's theory, they should fall with the one that's twice the mass, falling twice as fast. So it should hit the ground in half the time. Whereas Galileo's theory was they fall with the same acceleration, meaning that they're picking up speed as they fall. Acceleration is the rate at which speed is changing. And they would both hit the ground at roughly the same time. You don't have to do the experiment to know from your observations probably that Galileo was correct. And he did plenty of experiments himself to test and make sure he was correct. So we consider him the father of the scientific method because he decided we really need to test our hypotheses and theories and not just say, oh, it's a beautiful idea, it must be true. You know, like the Raiders are the best team in the NFL. It's a beautiful idea, it must be true. It was true 3 times in my youth. We haven't had a winning record since I've been in Nebraska. We were in the Super Bowl. I came to Nebraska.
You were all right in the preseason.
Okay. So, according to what I looked up, it was 1727 when he died. A student asked that earlier today. So, Isaac Newton. Isaac Newton built on the work of Galileo. He's very famous for developing his 3 laws of motion, for developing calculus, for developing our understanding of universal gravitation. He also did work in optics and a lot of other things. He was really one of the truly great minds in physics. If you want to hear me talk about him, you can listen to the recording from this morning's class on the YouTube channel when I get it uploaded, because I haven't had time to even eat lunch, much less upload the lecture. You guys do know that all the lectures get uploaded to YouTube. You can click on the link in the Moodle class and goes to the YouTube channel, choose the playlist for lecturers and watch the class. Well, watch this stuff and hear me, which, you know, is a wonderful, wonderful thing for nobody. Okay, Isaac Newton, just some things I didn't talk about this morning. Isaac Newton was a very religious man, and he wrote just about as much about religion and theology as he did about science. He also became a politician for a short period of time. And according to what I've read, and I'm no historian, he is on record as speaking exactly once in Parliament when he was a politician. And of course, him being the great man, he got to speak, and everybody was like, ooh, he's finally going to say something wise. And he said, Could we close the window? It's getting a little drafty in here. He was a very significant politician in his day. Okay, Marie Curie. Marie Curie, sad story, she died from the damage she received from doing her research in physics because you know what? They didn't know that radioactive materials were dangerous when she started studying them. They found that out, partially because, of the damage it did to her. One of the most honored families in the world, I think they had, both spouses got Nobel Prizes. I think one of the children got a Nobel Prize. And so she has really helped to advance our understanding of what's going on inside the nucleus of atoms. And so another important person, Niels Bohr, person who is one of the fundamental people in developing quantum mechanics. Obviously, Erwin Schrödinger gets a real large amount of credit for developing a wave equation. These are important people in the development of physics. This is not a history class, and when I was your age, I was really annoyed when the teacher spent time talking about the background and history of physics. I was like, I don't care who did what. I care how nature works. And then I took the graduate records exam, and they asked me these history questions, and I was like, I don't pay attention. It is important to me that you understand that our knowledge today has been built up by thousands of people who have done very hard research to develop from no knowledge to where we have, and that any discovery today is not simply that person came up with it, that person's brilliant. They might be brilliant, but they had to have all the people before them. Now, some of the jargon here, models, theories, and laws. A model is an analogy. A model isn't real. It is an analogy to help us think about something. So if we go back to when I talked about Aristotle, he had the model, he believed it was true, that the planets were doing circles on these spheres and that all the stars were on one big sphere that he called the celestial sphere. And so all the stars being on a celestial sphere, now we understand the Earth rotates, as he thought that whole celestial sphere was rotating around the Earth, and all the stars appear in the same positions relative to each other. So every time you look at the Big Dipper, it looks the same because the stars are fixed in those positions. Now, today we know that's not true. The stars are out there flying willy-nilly. They're so far away that the actual angular changes are really, really minute. And so it's useful for us to use the model of the celestial sphere. You can buy a celestial sphere physical model, a globe that has all of the dots for the stars marked on it, because it's useful for finding positions of objects. Even though we know it's not true, it's a useful model. So that's what a model is. It's not an idea of how it works, but it is a structure, an analogy to help you understand something. A theory is, an explanation of how things work. And when you go through the scientific method, you start by coming up with a hypothesis and an educated guess of how something works. And in this class, we want to really focus on the scientific method for lab. And so each lab, you're going to have an observation of something interesting you note. And that is pretty prescribed. Like today's lab, your observation has to be about things falling. And then your hypothesis has to explain why whatever your observation was occurred based on scientific ideas. Hypothesis, it's an educated guess. It is using scientific ideas to explain something that you don't know. Well, once you have that hypothesis, the next step of the scientific method is to test predictions of the hypothesis. Now, you don't go back and test your original measurement, right? Your initial observation. You have a hypothesis to explain why the initial observation works, but it should make other predictions. And so then you test predictions. And if you test a prediction and it turns out that, hey, that prediction was correct, you get more confidence in the hypothesis. If, on the other hand, you test it and it turns out that the outcome is not what was predicted by your hypothesis, you know your hypothesis was wrong. And so you go back and you modify that hypothesis, come up with a better version because now you know something that wasn't true. And that's what the scientific method is built on. You just keep reiterating, going over and over through that process, testing in different ways. And after you've tested enough, people start to get some confidence. And instead of calling it a hypothesis anymore, we call it a theory. So theories we have some confidence in, some more than others. Certain theories can be called laws. If you can put in a simple equation and it's generally true in a broad range of situations, like Newton's second law, the net force on an object is equal to the mass of the object multiplied by its acceleration, then we give it the name law. So 3 words there, model, theory, and law. And so I just talked about the celestial sphere model. Here we have the example of the planetary model. Second semester, when we talk about the atom, we will learn about Rutherford with his planetary model, where he said that the Earth goes around and the other planets go around the sun the way electrons go around a nucleus. And he didn't do it exactly the same, because he said they did circular orbits. Well, we know the planets don't do circular orbits. But right away, that model was known to have flaws. And so we had Niels Bohr that came up with a quantum model, and we moved forward from there. But the model is saying it's like this, an analogy, whereas a theory is explaining why it works. So some things that scientists do. Remember, I had the background of scientists. We get our ideas from other scientists, right? Scientists don't start with a vacuum of knowledge. Okay, I know nothing, let me learn this. They gather information from other people, work that's been done before, and then they test their ideas. They invent a hypothesis that they test, and when they've done enough tests that they feel somewhat confident, they publish a paper about it. And then you know what all the other scientists do? Yeah, they try to disprove it. They take it as their challenge, right? You don't just say, he's a great thinker, he must be right, or, well, she would never be wrong. They try to test these. I have heard some people, I think it's Priscilla Laws at University of Washington, who said that the reason there are many more men in physics than women is because it's so confrontational. You publish something and immediately everybody's out to show you're wrong. I tend to disagree. I don't like people to be confrontational with me, but that it is in that respect confrontational. People are going to try to test and see if you're right or wrong. Now, an example of science done wrong. Does anybody here know the names Fleischmann and Pons? Yeah, because I talked about great. Pons and Fleischmann thought that they had discovered cold fusion. That is, they left an experiment going overnight. They came back in the morning, and there was a big hole in the concrete where it burned through the floor. And they were like, we didn't put in enough energy for that to happen. It must have released its own energy. The only thing that could release that energy must have been fusion of hydrogen to helium. But they did it without high temperatures and high pressure conditions. That's like a holy grail for physics, right? If we could find a way to have nice controlled fusion of hydrogen into helium, releasing huge amounts of energy in the process, we could power the Earth without having to use any fossil fuels. We would just be releasing helium. It would be great. And so instead of going through the process, doing more experiments, writing an article and having other scientists test it, they call it a press conference. Because this is major. And so they call it a press conference and they tell everyone, hey, look what we did, blah, blah, blah. And it was, they were using palladium metal. So everybody went out and bought themselves a piece of palladium, tried to reproduce the experiment. No one could ever make it work. And of course, when you can't reproduce it, well, there is that Journal of Irreproducible Results, gives their Ig Nobel awards each year, but it's not good science, right? And so Pons and Fleischmann became famous for jumping the gun and not actually following the scientific method and embarrassing science a lot, because when you make a big announcement like this, we solved the world's energy problems, and then everyone says, hey, you're wrong, that's not good for science. Why do I have a blank page there? I do not know. A clicker question for you. So I have to, okay. I got to get my brain going. I got to remember how to change from one to another. Okay, so the clickers are now open. So second question, see if we can get more than 10 this time. At what point is the scientific method complete? When are you done? When have you proven yourself to be correct? Woohoo, we're up to 12. That's 2 more. 14. 15. 16. Excellent. Okay, I'm going to end the polling here. Well, 17. Wow, there are only 18 registered. That's pretty good because there's people in a different lab section. We had 16 people that said it's never done, and one said after you test the hypothesis. Now, I was not clear in answering this question when I went through it. I left that to your analysis pretty much, or to you've read it before. The scientific method is never done. You have never proven something to be correct. You can disprove anything with one experiment that shows to the contrary, but you can't prove it correct. It's a constant process. If your prediction passes this test, you go back and you test differently, and you just keep going through that, and people get really, really confident. So at this point, we all believe, I assume with 100% assurance, that if I let go of this ball, it's going to fall. It's not proven scientific fact, but nobody's going to say, no, it's not going to, because we've done the experiment so many times, so many different ways of testing it, that we have really strong confidence in it. All right, now a difference in accuracy and precision. Back to things from the lab today. We're going to be making measurements in lab today, and one of the things that is important to know is just the difference, the distinction between an accurate measurement and a precise measurement. So as an example here, we have the standard, targets. And if we were in the Olympics doing our archery competition, if you look at this, who would win the round? Okay, the one on the left. This one would win. Why do you win? Because you're more accurate. So this one here is accurate. Accurate means that you are close to the target. But this one here, they really had fine grouping. I am a real sports junkie. So yes, I watched team handball. I watched field hockey. I watched archery competition from the Olympics, which is why I'm so panicked today getting ready for class probably. And there was, I think it was an American archer who had a very tight grouping like this. But it really doesn't help you if it's not close to the bullseye. This here is precise. It's very reproducible, but it wasn't accurate. It wasn't close to the goal. Now, of course, your goal in anything is probably going to be both accurate and precise. But one of our real goals in lab today is to understand and to try to put numbers on just how close we are. How accurate are we to, or how precise, how reproducible are our measurements? So accurate is how close to the correct. Precise is how much they vary. We're actually going to be focusing more on precision. You can have something like a standard error. Let's say that I measure myself with a meter stick that's calibrated wrong. I can get really precise, reproducible results, but they're all wrong because the calibration's wrong. That's, an error that allows you to be inaccurate but precise. So whenever you're looking at any measurement, we're going to try to analyze how accurate and precise we are. This here is a graph trying to, let's just skip that. Very much later on this semester, we're going to be measuring water in a beaker. But this is an example to give us some uncertainty ideas. You probably have learned in a chemistry class when you measure the water level, not in a beaker, but in a graduate cylinder, that you measure it at the bottom of the meniscus. The meniscus is this curve instead of a flat line. Why does water have a meniscus in the graduate cylinder to begin with? Okay, I heard words surface tension. I heard something about potential. It comes down to whether water has a lower energy when it's touching water or whether it's touching glass. It has a lower energy when it's touching glass. And so in order to get to lower energy state, it actually climbs up the glass a little bit. And so you get this meniscus, and when you measure to the bottom of the meniscus. That idea to choose the same color. So when you measure the bottom of the meniscus there. Now, if I measure the water up to that red line, there's a little more water than what I measured. And so there is an error here. I'm going to be off. I have an uncertainty. And I need to estimate how much could I be off. Now, in this case, if I'm measuring to the bottom of the meniscus, I know that my volume is actually going to be a little higher than what I measured. And I want to try to estimate how big it is. Now, we're not going to try to estimate here what the actual value is, but you could look at this and say, well, it goes up about, each line's a milliliter. So it goes up about 1.5 milliliters on the sides. And if we were to approximate a straight, once again, using the same color is a bad idea. If we were to approximate that it has straight lines to make triangles, then we could say, okay, so we have about the area of a circle and then take half of that height for triangle, and that's how much additional water there is, and you could get an uncertainty in the water by looking at that meniscus. And so when you're measuring, if you're trying to be as accurate and precise as possible, you're going to go ahead and do that. You're going to calculate, how much could I be off? There's also, how accurate am I in reading this at all? I'm going to erase all this stuff here. So how accurate am I in reading this? I have that little dashed line to lead the eye. Obviously, when you're doing this in lab, you don't have the dashed line to help you out. But I look at this and I say, well, I have 31 below it, 32 above it. So it's between 31 and 32. How do you read that? I should totally call on somebody in that classroom, but I don't know their names. Okay, let's try this. You in the checkered shirt sitting over there on the side. Actually, he could be not in the class because he's not paying attention. Yeah, he must not be. Oh, bad call. Yeah, they can hear me. Everybody looked at him. Sorry. Okay. I'm not going to try. If I knew their names and stuff, I will just ask, and I don't know your names yet. I'll work on it today. In the red shirt in the third row, just what would you read? Larissa Bovey. What would you read this to be? It's 31 where the lower line is, 32 where the upper line is. What would you read it to be? For the water level. It's 31 milliliters here, 32 milliliters there. What would you say the volume is? Okay, so you'd say about 32. Anybody disagree? See, we're confrontational here. Okay, one row. Okay, is it Latif? No. Very wrong. Very wrong. Mahalo, what would you say? Okay, so she said between 31.8 to 31.9. Okay, there are some other hands after that. Do other people want to add in there? Okay, now I like Mahala's answer because she didn't just give a number, she gave a range. We know that we're not going to be perfect on this, right? And so she gave a range. I think it's between here and here. Now I look at this, and my personal measurement is I would have probably said 31.8. But then I would have said, I know that that's not perfectly right. It could be off by a little. And so I have to estimate how much could I be off. And so a rule of thumb that I learned to use is I'm pretty darn sure to within a quarter of the separation. And if I round a quarter to one digit, I round up to 0.3, which is actually not scientific rounding. You should know that when you round to the even if it's exactly 5. So 0.25 actually rounds to 0.2. Right. How many people knew that? Okay, good number. So I would say this has an uncertainty of somewhere around between 0.2 or 0.3. I always opt for 0.3 because I just don't have that kind of confidence. And so I would say 31.8 plus or minus 0.3. I have my uncertainty now that I estimated based on my ability to read this instrument. What else am I missing? The units. So I need to have my units there as well, milliliters. So one of the big things we're doing today is trying to go through the process of identifying our uncertainties and being able to assign them like this. What was my source of uncertainty here?
Limited ability to read the meniscus.
Okay, limited ability to read the meniscus. And then there was another one that somebody said, we have the actual meniscus, which means that I don't have a perfect position that I start with. Okay, we are going to measure today using Vernier calipers. This here, the calipers are that, right? The things that open and close, the jaws, if you will. The Vernier is named after a dude who came up with it, that thing right there. Now you should have, unless I took yours, Vernier calipers in the drawer at the end of your benches. And so you take these Vernier calipers, and when you want to measure something, I don't know how good the picture is, but this would be a reasonable place to switch over to using the camera where you can see me, so they can see me using the Vernier calipers. What are you doing, Jordan? Oh, yes, that's okay. Just don't worry about it right now. Better not to mess with their camera. Okay, so to measure something with Vernier calipers, first thing to note is, and I suppose maybe it'll work better if I turn the lights on now. If I close the Vernier calipers all the way, there's a gap right here. Not all of them have that gap. That gap is to keep them from binding up. You don't want to try to measure something in that gap because when it's closed all the way, it's still open. It means that's not the part you're measuring. So you take the thing you're going to measure. I'll take this pin as an example. Put it in the jaws here. Close it up so it can slide through, but it's tight. And then we're ready to look at the actual Vernier. And so now you can switch back to the presentation. I'm going to zoom in on a Vernier here. That's, well, it's going to be better if I erase. So here we have a Vernier that you should be able to see. And the markings, like that 3, that's measuring in centimeters. Now this also has inches. It's inches on this side. And we just don't use inches, so we ignore that side completely. The first line is your indicator of what the number is. So you look at that first line, you say that comes between 3.1 and 3.2. Well, if it comes between 3.1 and 3.2, your number is going to be 3.1 something. So I can read right off the bat that my number has to be 3.1 something. Now, the next part is the part where the Vernier name comes in, and it's important. What he did was he set up different scales for this grid compared to this one. If you look, that comes in at 3.1. This one here comes in at 4.0. The part that's going around the outside has 10 marks in the space that the inner part has 9 marks. So what that means is you have a 10% difference in the widths. And so when you look at them, you can see this 0 line doesn't match up with any line. It's just sitting there, it hits smooth metal. But as you move down, you get closer and closer to matching up. So in my estimation, this one here matches up the best with the line above it. Since there's the offset of 10% per line, and that's the 5th line, then that means that it was 50% off of 3.1 or 3.15. So I just look at this one. It was 0 I marked, 1, 2, 3, 4, 5. Since it's the 5th one, that makes my next digit 5. Now, that's a good measurement. How big is my uncertainty? We had things to limit the uncertainty. I had these calipers that close up nice and tight. And so I should have very minimal uncertainty in actually having the caliper set to the right size. And then when I measured this, we say, well, how much could I have been off? How many people think that this line would have been a better matchup? I'm sorry, yes. That's why I keep them off. Okay, so how many people think that one I marked would have been a better matchup? None? This is the one right above it. Or were you saying above that? No.
They were asking which one was. Your arrow was pointing kind of towards the same line.
Okay, it's pointing to that one there is the one I was asking about. How many people think that these two here match up better? So pretty much everybody agrees with me. But you can see they're close. So there's a chance that it could have been off by one in identifying which line lined up best. And so my uncertainty is 0.01. That didn't stand out so well. Change color again. So this allows me to get a smaller uncertainty because of the fine measurement. And then what's the last thing I need here? The units. And I said this one here, this one here is measured in units of centimeters. Now, sometimes you'll look on your Vernier calipers and it will say mm. And you naturally think mm should stand for what? Millimeters. But no, metric measure. It's really disappointing. Okay, so that's how we use the Vernier calipers. You're going to use the Vernier calipers today to make measurements. Next slide. Okay, error propagation. Since every measurement has an uncertainty, when you start multiplying things with uncertain values, your answer from the, doing a calculation is also going to be uncertain. And so if you want to calculate the correct uncertainty, these are the equations we use. Now, the lab has a section for you to calculate the density of your little ball bearing. And you need to do that. But then it says find the uncertainty in that density. You don't have to do that, but if you do it correctly, we'll give you an additional 5% extra credit on today's assignment, the lab. So to calculate that uncertainty, you have these rules to follow. If you have two things that are added together, so if I take my height is 6'3" plus or minus a half, 6'2"3/4 plus or minus a quarter inch. And I say, Jordan's height is 6'1" plus or minus a quarter inch. What's the sum of our heights? Well, if you do the sum of our heights, you're going to have an uncertainty, and that uncertainty is going to be the uncertainty in my height plus the uncertainty in Jordan's height. On the other hand, if we're multiplying or dividing, it gets more complicated. We take the uncertainty in one measurement divided by the actual number, plus the uncertainty in the next divided by its actual number. Those are percentage uncertainties, in other words. You add those percentage uncertainties, and you get your percentage uncertainty in your final answer. And if you have an exponent, well, the exponent is really just a special case of this. Because if I have x raised to the 3, that's x times x times x. And so the rule above would have given you the same answer if you just did it 3 times. So to find the uncertainty in the density, you'll have to use both of those relationships. And this is the only time in the entire year we're going to actually use these error propagation equations because it's a lot of work. You know what we do instead of that? Certainly you do. We use significant digits. Significant digits keep track of roughly your percentage uncertainty. And so we use significant digits as a much easier way to keep a rough propagation of uncertainty. And we will talk about significant digits in class later. I don't think I'm going to talk about them today. Nope, going to talk about it. I swear I thought I wasn't. I should have looked at every slide. Okay, significant digits, simple rules. A digit is significant if it's not zero. First of all non-zero digits are significant. 1, 2, 3, 4, 5, 6, 7, 8, 9. Zeros are significant in two cases. A zero is always significant if it's between significant digits. So for instance, in 101, the two ones are significant, so the zero in between must also be significant. Zeros are also significant if the value won't change if you remove the number. So if I have, like if we look here, 100.0, if I remove the last zero, the number won't change. So why do I put the zero there? Because it has meaning. Because it means I know that that value is zero. If I take that away, then I'm saying I don't know what the next digit is. But I put that zero there, I know what the digit is, it's zero. So this is significant. If I were to remove, okay, this one here is a little less. If I remove this zero, it would make the number change, but that one's not significant. That's why we like to use scientific notation, because that's just a placeholder to move it. If we use scientific notation, this would be 1 times 10 to the minus 3, and it would be clear. Scientific notation is wonderful. Every digit is significant in scientific notation. So if we look at these, how many digits do we have significant in the first number? 3. How many in the second number?
4.
And the last one? All right. So that's pretty simple. Now, when you add numbers, it's a different rule than when you multiply numbers. What I found is most students, when they come into this class, they know the multiplication rule very well, but they don't know the addition rule. So the addition rule, when you say all the words, it really sounds nonsensical. The greatest of the least significant digits is the least significant digit in the answer. Yeah, exactly. It doesn't seem to make sense, right? But if you do it, if you actually do the math, it turns out to be pretty simple. So let's take this addition problem that I put. I have 1, 2, 3 plus 1.2 plus 3, 2, 1, 0. For each one of those numbers, I'm going to identify the least significant digit, which means the farthest digit to the right that is significant. So in the first number, 1, 2, 3, 3 is my least significant digit. So I'm going to put a line over that. The next one, 1.2, the 2. Finally, the last one, 3, 2, 1, 0. The what?
Oh, I'm sorry, it's up there.
Yeah, I'm sorry. Yeah, I have.
Number 2.
Okay, so it's the 1 here. So if we look at these, which one of those least significant digits is in the highest position? The 2 is in the lowest position.
The 3.
3 is in the middle. The 1 is in the highest. And so that means the 1 is my least significant digit, my greatest of my least significant digits, and so that's going to be the least significant digit in my answer. So when I add these up, my answer is only significant out to the greatest one, so it's only significant out to that 3. So the correct answer to this would be 3, 3, 3, 0. That's a 3 in front. Because the 4 and the 0.2 were not significant when I add them up. Now, a lot of people would have tried to use the multiplication rule. The multiplication rule is you just take the least number of significant digits in the numbers. So looking down here at the bottom, how many significant digits are in 1, 2, 3? How many in 1.2? How many in 3, 2, 1, 0? And so when you multiply them, the smallest of these numbers is 2, and hence I have 2 significant digits in the answer, so the answer would be 470000. We use these because these other digits here, we can calculate them, but they're not really meaningful. I would have needed to have additional digits here to make them meaningful. Question, Jordan?
If you round up to say that, or say if in 47367
or yes, 7, 6. If the 3 was a 7, would you round up to 48?
Well, the rounding is like you learned in first, third grade, whatever, except for when it's exactly 5. And when it's exactly 5, then you round to an even number.
Okay.
So if it was 47500, then I would round to 48. If it had been 48500, I would have also rounded to 48. Okay, any questions about that very quick significant figures and how to keep track of them? The first exam will have a question where you simply have to do significant figures. Do you have a question, Maranatha? Yeah, okay. I think I said that wrong. I think I said it wrong when I talked about the placeholders. If the 0 is only a placeholder, it's not significant. And so those zeros, it's 470000. Those are just placeholders, so they're not significant. Did that answer it? Yes. Okay.
How would you know that? If you had basic
I still didn't hear you.
if you had like
Okay, what if I have 3 significant digits, but the last one is a 0 and it looks like a placeholder? There is, an ambiguity. Like you look at my 3330. I said that was 3, and that's why I put the 0. But if you just saw it, you wouldn't know if it was significant or not. There are a couple of ways of indicating it. One is if you put a bar over it. So like if I put a bar over this 0, that means that 0 is significant. And thus the 2 in front of it have to be significant because they're between significant digits. If it's the last 0, if I put a decimal point here, that indicates that the preceding zeros were significant. So there's 2 ways of marking it. Okay, lab reports. Today will be the first lab. It'll be your first lab report. There is one change. I took this from last year, and I just combined these and called it the scientific method. And that's 20 points. Hopefully you looked through the lab guide and saw this before coming to lab. But just going over the things you need to have in your lab. First of all, you don't have to have a specific lab book. You're going to turn in your labs by uploading PDF files to Moodle. If you have questions about how to do that, there are instructions in the lab guide, but you can always contact me and I can try to help you out. The first part of your lab just needs to be the header that says the title of the lab. So you look today and the title is measurements. So you put measurements. And then you have name and date. Now the name is not just your name, it's your name and your partner or partners if you have to have multiple partners, names. And the date you did the experiment. The reason we want the partners' names is so when the reports are being graded, the grader can gather together the reports from each person and grade all the partners at once rather than doing this one, then spending a lot of time then doing another one that should have the same data, save time by doing it together. Equations. List each equation you're going to use in the lab. Today we're not doing any equations. When you have an equation, make sure you put definitions of what they mean. So for instance, if I was using this equation, Newton's second law, I'd say F equals force on object. Of course, the sigma just means sum of. You don't need to define what mathematical symbols mean. M equals mass of object. And A is the acceleration of object. So you need to have the equation written out and what the symbols mean in the equation. And then in your write-up later on, you need to show one example of using the equation. Don't show 10 times doing the same calculation, right? If you can show it once, I'm sure you can do it 9 more times. Just show it once so we can see that, yes, you knew how to put it together. Questions? Okay, what does the arrow mean? This arrow means that it's a vector. It means that we have not just the magnitude of the force, the magnitude is the size, but it also has a direction with it. Okay, so that's the equations, 5 points there. 5 points for the apparatus. Pretty much you can just look in the lab guide at the apparatus, list them out, and draw a picture. For our lab today, you know what we're doing? We're dropping a ball. What do you draw for a picture? I got a ball. Here's a meter stick. Here's the ground. That's about the best I can do, right? It's not a very sophisticated picture. But later on, when we're using more sophisticated equipment, a diagram really makes it so a person can see this is how the things were put together. Then we have the procedure. Now, in the lab report, we have all kinds of nitty-gritty detail. I put that in there because I don't want people to make mistakes. I want to answer every possible question a person can have. When you write down your procedure, or someplace I called it, I used the word that started with E, I don't know what it is. When you write down your procedure, do not just copy the procedure from the lab guide. I want it to be brief and yet enough that a person could reproduce it, right? So I put in lots and lots of detail so you won't make mistakes. You don't need all of that detail, but you need to have enough there that a person could reproduce it. And I will give you an example for today's in the next couple slides. Then we have the data, calculations, and discussion. This is where you actually did the experiment. Surprising that's only 1/5 of the grade for the actual experiment, I know. When you do this, this actually should be a running commentary on what you did. So you start by saying, okay, going to drop the ball 1 meter. Then you drop the ball 1 meter, of course. And you put a table, make a table so you have things like, the trial. I'm going to use abbreviations because I don't have much space. And you have the time. I'm going to put things in there. If I put a measurement, what things do I need with the measurement? I need units and uncertainty. Sig figs is related to that. And so when you're putting a table, if they all have the same uncertainty in use, you can just put up here plus or minus, 0.01 seconds or whatever my uncertainty is. And then it's understood that everything below has that uncertainty in that unit. And then you just put your data, so trial 1, trial 2, etc. You put them in the table. It has a glance factor. Anybody can look at your data table and see, their data did this. Some people like to write it out in sentences, and you can't figure out what happened without doing a whole lot of reading. We want to make things as brief as possible. Brevity is an important thing. Don't write super long reports. Use your words concisely, unlike anything I write. Okay, so I then did my experiment. I made my measurements. And let's say we had something went wrong, like one of them bounced off the foot. One of them bounced off the foot. Had to redo it. You put in those kind of comments, things that went wrong, as you're going along so people can see. If you make a measurement, and like I do, 0.732, 0.651, blah, blah, blah. And then I have, 0.031. That 0.031 is wrong, right? Don't erase it. That is very bad scientific procedure. I have known people who did that, but it's not science. You have to acknowledge your data. But if you know it's wrong, you don't pretend it's right. You leave it there so people can see you had it, and then you just draw a single line through it and say, hit button twice or something, something to explain why that data is bad. So people can see that you had the bad data, but they know why you think it was there. Part of the reason this is important is sometimes you do an experiment, you think you know what's going to happen, something different happens, you think it's bad data, but it turns out that you just discovered something that nobody knew. That's happened many times. So you don't just throw out the data. You keep it there, just put a line through it. That's why traditionally when you're doing science, you should always use a pen. That way you're less likely to erase it. And then I have the students go, I got an erasable pen. Hey, best of both worlds. Okay, the results, calculations should be shown there in the data calculations discussion section. Just do the calculation, say, here's calculation, boom. The results should only summarize things that have already been shown. So results has nothing new except for when you're doing percent error difference, which we're not doing today. So today we're going to be dropping a ball 5 times. You're not going to show the times for each one to fall. Just show the average time it took for it to fall. That's a result. So for your results, you're going to have the time for your ball to fall 5 times, time for your partner's ball to fall 5 times, the time for it to fall 2 meters, the average there. Those are the things you're putting in the results. And then finally, the conclusions. Conclusions is where you show what you learned in the lab, what went wrong, what could have gone better, and where you discuss the outcome of the test of your hypothesis. So your hypothesis, it's specified in the lab, your hypothesis test has to be done by comparing the time it takes for a ball to drop 1 meter to the time it takes for a ball to drop 2 meters. So you get down here to the conclusions. You had a hypothesis that made a prediction about how those times would compare. In the conclusion, you're going to say, okay, so my hypothesis was either backed up because this happened, or my hypothesis was disproved because this happened. So you don't just say my hypothesis was confirmed or disproved. You give the reasons why. So the conclusions is where you show what you learned if the lab actually met its purpose. And, if you have suggestions for things to make it better, put them in there. I told the TA, if students give suggestions to make it better, let me know, because every year I revise the lab guide. Any questions on this page? All right, so here is my abbreviated procedure, right? If I was doing the lab guide, I would write something like this. I'm going to estimate the time for the ball to drop 1 meter. Now, notice in the lab guide, it gives you a lot more details, like make sure you do this before you drop the ball. Why? Because we want you to actually think about how long do I think it is without actually being biased. Then you'll drop the ball a few times, and you'll modify your estimate and explain why you changed it or why you left it the same, and estimate how much error you think you could have. When you estimate how much error you think you can have, don't just say, I think I could be off by 0.2 seconds. Give reasons why you came up with that number. If you just give a number without the reason, that's not going to be good enough. By the way, there are questions interspersed. They all have a bold Q-C for question/comment. Make sure you answer all of those, and don't just say, some of them are yes/no questions. Don't just answer yes. Don't put Q-C3, yes. Make sure that your answer makes sense to somebody who's reading your lab guide without having your lab report without having the lab guide. So we need to say, yes, this happened. Oh, the computer's ready? That's right, I need to give you one. Actually, you can go through the back door. That's our lab TA, Yafet. Can't remember either of his last names right now, so I won't say them. Okay, going on then with the experiment, then you're going to measure the ball dropping 5 times. We have computers that have a timer that measures out to the thousandths of a second. If your phone has a timer that measures out to thousandths of a second, sure, feel free to use it. But if it only measures out to hundredths of a second, then we want to use the computer one because it has one more digit. The timer on the computer is really simple. You hit the space bar and it starts. You hit the space bar and it stops. You write down the number. When you hit the space bar a third time, it clears and starts. So you don't have to do a clear cycle. Okay, so there's 5 measurements for you and 5 for your partner. So let's suppose that being in the front row means getting called on a lot, especially if I ask another name. So Gila and I are partners. So for my data, Gila's going to measure the ball 1 meter off the ground. Now, a meter stick, so this is the 2 meter stick here. For the 2 meter stick, many of you might need to go higher to drop it, but it's not good. I'll grab it from over there, rather than have you throw it across the room. So if I'm working with Gila for her measurements, I'm going to be standing out here, and I'm going to hold the ball 1 meter above the ground. Say, you ready? Yeah. And so then I will drop it. She will start the timer when it leaves my fingers, stop the timer when it hits the floor, write down her number. That's her measurement. I'm going to record her measurements as well as mine, but that's hers. So in your book, make sure you have one column that's my measurements, one column that's my partner's measurements. So her measurements are when she starts off the timer. Then when we reverse positions, she drops it, and I start, that's my measurements. So you're going to do 5 each from 1 meter, and then you have to do some from 2 meters. Now, I did not specify the number of measurements you need to make from 2 meters. But don't do just one. Because how would you know if you made a mistake? You don't have anything to compare it to. The reason we use multiple measurements is to make sure that our measurements are reproducible. What was the term we used for reproducible results? Precision. To make sure we have a fair amount of precision in our measurements. If you just do one, you have no idea. You could have been way off and just don't have a clue. So that will conclude the dropping part. Answer your questions there. Another blank page. Imagine that. Oh, wait. There was something on this page. There really was. This was procedure 2 on this page. Procedure 2 is measuring the diameter of the ball. Each partner needs to measure the diameter of the ball multiple times using the Vernier calipers, as well as trying to use a meter stick. Now, what's the difference in using the Vernier calipers and the meter stick? The meter stick, you have all kinds of problems to deal with. Things like, if I look at a different angle, we call that parallax, you seem to get a different value. You have the rounded edges. There's all kinds of problems with measuring the meter stick. What's that going to do to your uncertainty? It's going to raise it up. And so the reason I'm having you do that is for you to think about, what is my uncertainty trying to measure this on the meter stick? If it was a nice square object, it would be a smaller uncertainty. Because it's curved, it's a bigger uncertainty. And you might think of ways to reduce that uncertainty. Then you're going to measure it with the Vernier calipers. And so that's what the procedure 2 is. That's supposed to be on this slide that's blank. I don't know why it's blank, obviously. Procedure 3 is going to be to calculate the density of the ball. And this is the last instruction of the day. To measure the density of the ball, we need to measure the mass. So to measure the mass, we come up here, instead of trying to measure the mass of that little ball, I'm going to measure the mass of this thing that says 100 grams. The first thing I need to do when I measure the mass is I need to make sure that my triple beam balance is 0. Now, I know you can go like to chemistry lab and they have nice little electronic balances, right? I don't use those for a very simple reason. This illustrates good physics. We're using lever arms. We move the mass out. It creates more torque. We're creating counter torque with this. And we're basically using a torque balance. So I use them because it has the physics illustration in it. So first thing you need to do is make sure that with each one of these little masses in the little divot, and with the slider as far left as it goes, that the indicator points to 0. If it doesn't point to 0, and I'm going to change it so it doesn't point to 0 now, you adjust it by moving the screw out here, in or out. If you move it out, you have a longer torque arm. It's going to raise this up, as you can see. If I screwed it in, it would have lowered it. Once you have it 0, which it clearly is not now, so if you come up to use this balance, and you see there's balances around the room. If you come up to use the balance, make sure that you 0. Don't trust the person in front of you. They might not have known what they were doing. Then I put this here on the center of the pan. First take the biggest one, the hundreds, move it out 1 notch. It's still pointing above 0, so I'm going to try bringing it out 2 notches. Now it's pointing below 0, so I know it's going to be between 100 and 200. So I back off to the 100. Then I take the next one, slide it out to each setting, and how much did I say this thing was supposed to be? Oh wait, I made it way off calibration, that's why. Like, that's ridiculous. Or maybe it's 100, okay, it's between 100 and 110 according to what I have so far, and then I slide this last one. Now the last one, it's measuring in grams, and then it has marks for tenths of grams. Well, when I get this thing adjusted so the indicator points right at 0, I have my measurement, and just like before, if it measures tenths of grams, I need to estimate how far I am between those tenths of grams. So I'm going to estimate the digit for the hundredths of grams. And then I need to have an uncertainty for that hundredths of grams. Depending on your confidence, you could be as uncertain as 0.02 grams. Or if you're lean, you go 0.03 grams. Or if you're really not confident, you go to 0.05 grams. But you need to measure out to the hundredths, and your uncertainty better be somewhere between those numbers. Right? The uncertainty is based on your determination. Yes.
Southwestern able to see your, were you, or you didn't need to show it to them?
I figured I didn't set up a Zoom beforehand because we were in such a rush, and so I couldn't zoom in on that.
Okay, that's fine.
That's why I didn't.
No problem.
They wouldn't have seen.
And they're not showing right now either, I don't know. if they're-
That's true, they're not.
Did ask them, are they still there? Ask them
They're not connected anymore.
at all?
Hmm.
I've heard them. Ask them.
Oh, maybe they're. Okay, well,
They're there.
anyway, I don't see them. I've already gone through the lab, so what we're going to do now is I'm going to give you like a 5-minute break. When you come back, we're going to take a little test